Well, thanks for tuning in. The title of this talk is Pseudospectral Shattering, the Sine Function and Approximate Diagonalization in Nearly Matrix Multiplication Time. My name is Jess. I'm a graduate student at the University of California, Berkeley, and this is some joint work with Jorge Garza Vargas, Archit Kulkarni, and Nikhil Srivastava. So let me start with a definition. We say that a complex n by n matrix is diagonalizable if we can write it as V times D times V inverse, where V is an invertible matrix whose columns contain the right eigenvectors of A, and D is a diagonal matrix containing the eigenvalues of A. Now, for those of us used to working with Hermitian matrices, this definition might seem a little unnecessary. After all, every Hermitian matrix can be written in this way, with V in fact chosen to be unitary. But as we'll see at several points during the talk, the case of non-Hermitian matrices is quite different in a number of ways, the first of which is that not all non-Hermitian matrices are diagonalizable. Now, along with this definition comes a computational task that I'll set up in the following way. Given a complex n by n matrix A with operator norm at most 1 to keep things normalized, and an error tolerance parameter delta, we want to find V invertible and D diagonal so that A is delta close to VD inverse in operator norm. Now, when I first heard of this problem from my co-authors, I said to them, surely this must already be settled. After all, thousands of practitioners are calling EIG in MATLAB this very minute. And for practical applications, the nice thing about this problem is that, you can always check whether an algorithm has solved it correctly, just by testing how close A is to the VD inverse that the algorithm spits out. But amazingly, rigorous analysis of commonly used algorithms in floating point arithmetic, and in particular of their convergence, has mostly remained elusive. And our main result today is in this spirit. So it goes like this. Assume that there is a numerically stable algorithm for multiplying n by n matrices that runs in time mm of n. So you could take this to be the naive n-cubed algorithm or something more elaborate like Strassen, whatever you like. But given that you can multiply matrices numerically stably in time mm of n, there exists a randomized algorithm for the approximate diagonalization problem, which uses on the order of mn of n log squared n over delta arithmetic operations, log to the fourth n over delta log n bits of precision, and succeeds with probability at least 1 minus order 1 over n. So over the course of the talk, I'd like to give some background on the problem and sketch out the algorithm we study, which is basically a small modification of a classic algorithm for the field. We're going to work in the setting of finite precision arithmetic, which means that every number our algorithm sees is stored up to some machine precision mu. But instead of precisely analyzing the rounding that this model of computation entails, we'll take a pedagogical perspective that after every operation in the algorithm, an adversary can come in and make bounded size modifications to our data. And the size of these adversarial perturbations is controlled by this machine precision mu. So before we move on, I want to survey briefly some of the prior literature on this problem in the finite arithmetic setting. There's also lots of prior work in rational or exact arithmetic that I won't have time to discuss. In the Hermitian case, this problem is extremely well studied. Work of Hoffman and Parlett in the 60s and 70s, as well as Wilkinson, showed that the shifted QR algorithm can solve this problem in roughly n-cubed time. And from some more recent work of Ben Orr and Eldar, we know that a single eigenvalue can be found in time mn of n. Again, this is the time it takes to numerically stably multiply two matrices. Our result still improves on the n dependence here, since there is an additional factor of n necessary if you want to find all the eigenvalues instead of just one. In the non-Hermitian case, on the other hand, much less is known rigorously. And I want to direct your attention mostly to a beautiful paper of Armentano et al. From 2018, which showed that in time n to the 10 over delta squared, at least in terms of arithmetic ops, one can diagonalize the matrix A plus delta Gn, where Gn is IID standard Gaussian entries. Now, this Gaussian preprocessing step was crucial in their analysis, and it'll be crucial to us as well. So the reason we're able to obtain nearly matrix multiplication time is that we reduce our algorithm to the following 3 subroutines. These are matrix multiplication, inversion, and QR factorization. And from some papers of Demel, Dimitriou, Holtz, and Kleinberg from 2007, we know that each of these three primitives can be done as fast as numerically stable matrix multiplication. Now, before we get to the algorithm proper, I want to talk a bit about what makes this problem hard. And the key observation here is that, unlike in the Hermitian case, non-Hermitian matrices are spectrally unstable. In other words, small perturbations in the entries can cause very large changes to the eigenvectors and eigenvalues. And given that we care about this problem in finite arithmetic, this requires us to take extreme care even with the small errors that we incur along the course of our algorithm. So let's do an example. Consider the matrix Jn of epsilon, which has ones on its superdiagonal, epsilon in its lower left-hand corner, and is zero otherwise. Now, it's easy to check that the characteristic polynomial of this matrix as a polynomial in the variable z is equal to Zn minus epsilon, which means that its eigenvalues are the nth roots of epsilon. So in other words, an order epsilon perturbation to the matrix changes its spectrum by order epsilon to the 1 over n. Microscopic errors can have macroscopic implications. And if you remember back to the second slide, our main theorem concerns the so-called backward error version of the diagonalization problem, namely that I want the exact eigenvectors and eigenvalues of a matrix close to the one I started with. And this example illustrates why, if you want an algorithm that runs in finite precision, backward error is the best that you can hope for. After all, there are matrices, like the one in the example here, where you need exponentially many bits of precision to actually approximate the true eigenvectors and eigenvalues, instead of just finding the eigenvectors and the eigenvalues of a matrix nearby. Now, this spectral instability is a key obstacle in analyzing any algorithm to solve the approximate diagonalization problem. And there are a number of ways that you can quantify it. But I want to highlight one in particular that we found very useful in our analysis. This is the so-called pseudospectrum, which is a family of subsets of the complex plane indexed by a parameter epsilon greater than 0. Given a matrix A, we define the epsilon pseudospectrum as the set of all eigenvalues of all matrices, epsilon close to A and operator norm. So this is a set in the complex plane that tells us where the eigenvalues of our matrix can go after arbitrary perturbations of size epsilon. And it's a nice and useful lemma, one that I won't have time to prove, that we can also write this set as a level set of the resolvent. In other words, it's the set of all z in the complex plane for which the operator norm of z minus a inverse is at least 1 over epsilon. So here I've drawn two cartoons of the pseudospectrum so you can get a sense of what it looks like. From the level set definition, it's clear that the pseudospectrum always contains the spectrum, which I've drawn in pink in these pictures. On the left is the Hermitian case, whereas another exercise, you can check that the epsilon pseudospectrum consists of disks of radius epsilon centered at the eigenvalues of your matrix A. On the right is the non-Hermitian case, where the epsilon pseudospectrum in general can extend much further from the spectrum and have all sorts of interesting geometric structure. Now, as I mentioned earlier, our algorithm starts with a pre-processing step. And the purpose of this is to tame the pseudospectrum in a certain sense. So we'll say that the epsilon pseudospectrum of a matrix is shattered with respect to a grid G in the complex plane. If the pseudospectrum has n connected components, this is an n by n matrix, and each square of the grid contains at most 1. So here's what that looks like. You can see here's the grid, and here's the 6 eigenvalues of some matrix, and the blue represents the epsilon pseudospectrum. So each connected component of the pseudospectrum lies in a unique square, and no square has more than 1 component. Now, our pre-processing result says informally that by adding IID complex Gaussian noise of variance 1 over poly n to the entries of any matrix, one can compute an epsilon of size 1 over poly n and a grid with squares of size 1 over poly n, so that the epsilon pseudospectrum of the noised matrix is shattered with respect to the grid. Once we do this, we'll pass both the noise matrix, epsilon, and the grid to the algorithm. So the reason why it's important to pass this kind of augmented data structure to the algorithm is that once you know that the epsilon pseudospectrum is shattered with respect to a grid, you have a couple other pieces of information as well. So first, you know that after perturbations of size epsilon, each eigenvalue of the resulting matrix is in the same grid square as it started in. Second, exercise, if you make a perturbation of some size delta less than epsilon, then the epsilon minus delta pseudospectrum of the resulting matrix will be shattered with respect to the same grid. So this is going to help us analyze the eigenvalues of the matrix, even when there's small errors that we incur over the course of the algorithm. Okay, so this is how we pre-process, but how does the algorithm work once we do so? So we analyzed a variant of a classic algorithm that I believe is due to Beavers Jr. and Denman from the 70s. As I just said, our variant takes as input A, epsilon, and a grid, together with a promise that the epsilon pseudospectrum of A is shattered with respect to the grid. So A here is the noised matrix, remember. So once you give the algorithms these three things, it proceeds in a couple of steps. So the first is we want to split the spectrum of A. So this means that we want to find two subgrids, G plus and G minus, of the input grid, each of which contains at least n over 5 eigenvalues of A. And it's a pleasant geometry lemma that you can always find a split that has this guarantee. Second, we're going to do a so-called deflate step. And this means that we are going to block diagonalize A to form two matrices, A plus and A minus, each of which has as its spectrum the eigenvalues from one of the two subgrids, G plus or G minus. Third, we're going to recurse. So now we're going to compute the eigenvectors and eigenvalues of A plus and A minus. And using these and our block diagonalization, we're going to recover the eigenvectors and eigenvalues of A, as is shown on the screen. So at the end of the day, we're able to ensure that A is delta close to VDV inverse and operator norm as desired. And remember that we started this whole game by doing a pre-processing step where we took our initial matrix and we added a little bit of Gaussian noise. And the reason why that's kosher is that as this guarantee at the end reminds us, all we want is for our matrix to be close to VDV inverse, where VDV inverse are the things that come out of the algorithm. So if we first take the matrix we're truly interested in and add a little bit of noise, and then to the noise matrix, add that to the algorithm and find VD and V inverse close to it, the result is going to be close to our initial matrix. So I've swept a lot of the hard analysis of this algorithm under the rug in the overview I just gave here. And I'm not going to have time to discuss all of it, but I do want to zero in on one crucial subroutine that's important for both the split and deflate steps above. This subroutine is the computation of the matrix sign function. So if you're not familiar with this object, to define it, let's let A be a matrix and assume that A can be diagonalized as in the first equation here, where D plus contains all the eigenvalues with positive real part and D minus the ones with negative real part. Then the sign function of A is obtained by replacing D plus with the identity matrix and D minus with minus the identity matrix and multiplying V and V inverse on either side. In other words, sign A has the same eigenvectors as A, but we've replaced each eigenvalue with either 1 or -1 according to the sign of the real part of that eigenvalue. And this may seem like a funny definition, but it turns out that sign A contains lots of very important information for both the split and the deflate steps of the algorithm. So first, the trace of sign A is exactly the number of eigenvalues in the right half plane, the ones with positive real part, minus the number in the left half plane, the ones with negative real part. And this is useful because if we're given a matrix A and a grid, by computing sign of R minus A, where R is like the horizontal shift of some grid line, we can figure out how many eigenvalues lie on either side of that grid line. And then we can execute a binary search over the grid to bisect the spectrum in the way that the sign or the split step demands. Sign A can also help us with the deflate step, although I actually won't have time to discuss this in detail. So sign seems like a really good thing to be able to compute, but how do we compute it without knowing the eigenvectors and eigenvalues? After all, the definition I gave here is defined in terms of V and D, the things that we're running the entire algorithm to try and discover. Well, Roberts in the 1980s, and I think 1980 exactly, introduced a beautiful iterative method for computing the sine function. So here's how it goes. We're going to set a0 to a and repeatedly set ak plus 1 to be half ak plus ak inverse. And Roberts showed that in exact arithmetic, this converges to sine of a. However, showing that this still holds in finite precision arithmetic has been open since 1980, and solving that problem was a critical step in our paper. In particular, what we need here is a numerically stable version of Roberts' result that says that this convergence still holds if at every time we apply a function, or every step of the algorithm rather, there's small adversarial noise that we are incurring. So with my remaining time, I want to sketch the key idea from our proof of this convergence. Let's write f of z for the function that we're going to repeatedly apply to our matrix in the Roberts iteration. And let's study a particular set of families, particular set of circles in the complex plane. So since antiquity, I think, it's been known that the set of points in the plane with a fixed ratio of distances to two focal points forms a circle. This is due to the geometer Appolonius of Perga. So the family that we're going to study is a family of circles in the complex plane whose foci are the points 1 and -1. We can parameterize this family of circles by the ratio, which we'll call alpha, of their distances to these 2 points. We're going to define C alpha plus to be all those points in the complex plane whose distance to the point 1 is at most alpha times their distance to the point -1. And similarly, C alpha minus is those points whose distance to the point -1 is at most alpha times their distance to the point 1. And as alpha goes to 0, these circles are going to shrink down around the points 1 and -1 respectively. So here's what they look like. You can see here is C alpha minus and some further circles for smaller values of alpha. And similarly, here's C alpha plus, and you can see the circles shrinking as alpha gets smaller and smaller. Now, the function f actually has a lovely geometric action on these circles. So it maps the circle C alpha plus to the circle C alpha squared plus, and the circle C alpha minus to the circle C alpha squared minus. This means that if all the eigenvalues of A are inside the union of C alpha plus and C alpha minus, so they're all inside these outer circles here, then the eigenvalues of f of A will lie inside the union of C alpha squared plus and C alpha squared minus, these two smaller circles. And so, in other words, if you keep applying f, the eigenvalues in the right half plane are going to shrink down towards the point 1, and the eigenvalues in the left half plane are going to shrink down towards the point -1. And this is exactly what we want the sine function to do. So this is all well and good, but remember that we needed a robust version of this convergence that says if you make some small perturbations in between every application of the function f, you still get convergence of the eigenvalues in the desired way. So the key step in our argument was to show a pseudospectral version of this result. So assume that the epsilon pseudospectrum of A lies inside the union of C alpha plus and C alpha minus. What we show is that for some alpha prime smaller than alpha, the epsilon prime pseudospectrum of f of A lies inside the union of C alpha prime plus and C alpha prime minus, for some epsilon prime a little smaller than epsilon. So in other words, the epsilon pseudospectrum is in these two circles, and we show that after applying the function, some epsilon prime pseudospectrum is going to lie in some smaller pair of circles. And now by carefully tracking epsilon and alpha as we repeatedly apply this function, we can show that the pseudospectrum of our iterate matrices is shrinking down closer and closer to the points 1 and -1. Thus, we're going to get convergence of the iterates to sine A even after we add a little adversarial noise in between each application of the function f. Because remember that the pseudospectrum tells you exactly how the eigenvalues of your matrix can move after a small perturbation. And if the pseudospectrum is shrinking down to 1, that means that the convergence of the eigenvalues of these matrices to 1 and -1. In other words, the convergence of this sequence of matrices to the sign function of the initial matrix is robust to small perturbations. So this is all the time I'm going to have for today, but I want to encourage you to carefully read through the paper if you'd like, to attend the live talk, and please reach out to I or one of my co-authors directly if you have any questions or comments. But thanks a lot for tuning in.